So from that one, that's going to take us into our lesson for today. We're going to look at these two patterns. We've got pattern A and pattern B. It's your job, looking at these patterns, you're going to come up with a function. You're going to claim what type of function it is. And then you're going to look at how it grows in the table. And then you're going to make like an observation. Which one's growing faster? That's it. So on your notes, you'll find the table. But go through that order. Explain how it's growing, which it's telling you here a little bit. Write a function. State what type of function it is. Then show how it's growing in the table. With your partner, this should take, 5 minutes. So let's take a look here. I'm going to start with the equation for both. Who can tell me what they're seeing in the pattern to get the equation that they got? Grant, for A, what are you seeing?
I got n to the second.
Okay, but what do you see? So we're going to do y equals n to the second. Or f of n equals, actually. It shows function notation in the table. So you're seeing n squared. What about the picture tells you n squared?
That it just keeps on going. It just keeps on multiplying
By itself. So, okay, by the step 2 by 2, 3 by 3, 1 by 1, 0 by 0. Okay, so we've got a square. Just for fun, I'll pause the video. So we're back here. We got f of n equals n squared. Let's go to pattern B. Who can tell me how they see pattern B changing? Micah?
I see it doubling.
1, 2, I got 2 of those. I got 2 of those. Doubling, right? So what's our function?
I want to say that it's equal to 2s, but the only problem is that I see that 1.
No, because that would be 6 here then. And that's
Or not 2s.
that's 8. It's not, can't be 2s.
S being 1 of s squared.
S squared would be side squared are these, not doubling. What are you thinking, Spencer?
Y equals 1 times 2 to the n.
Initial value times doubling growth factor to the n. You can drop the 1 and it's the same function, by the way. If you have 2 to the n, same function.
But step 0 is 1.
Well, yeah, what's 2 to the 0?
Start off with 1.
So you can. I like the 1 there because we're used to the initial value thing. But if you drop the 1, 2 to the 0 is still 1, right? It's just times 1, which doesn't change the answer because you have to do the exponent first, right? No matter what we do here, times 1 is just itself. But I like the AB. This goes the AB to the X route, right? Okay, so now let's build our tables. So step 0, I had 0. 1 squared is 1, 4, 9, 16, 25, 36, 49, 64. And if we're doubling, I had 1, 2, 4, 8, 16, 32, 64, 128, 250, 6. Okay, and on the bottom of your notes page it says, how would you explain how these are growing compared to each other? How would you explain how these are growing compared to each other? So we can all see the outputs. I think we should have more hands up than a few here. We can all see the outputs in the tables. How would you explain how they're growing compared? Owen? What would you say?
For pattern A, it's quadratic because
Yeah.
because it's like something to the power of 2.
It's quadratic to the...
Variable to the power of 2.
Yeah, what is B then?
It's exponential. Because
Yeah.
it's 2 to the power.
So I'm also going to show you how you know pattern A is not exponential. To be exponential, we would need a common factor, right? Can we do 0 times something to get to 1? No. And 1 times 4 is 4. Is 4 times 4 6 or 4 times 4 9? No. So that tells us right there, not exponential. To be exponential, we need a common factor. So maybe it's linear. We need a common difference. Plus 1, plus 3, plus 5. Is that a common difference? No, but what this does have, that does prove it, is it has a common second difference. Okay? That second difference being in common tells us it is quadratic. All right? Let's go to the exponential. Do we have a common factor? Times 2 times 2 times 2 times 2 times 2. That's why that is exponential. Notice our common difference would be 1, 2, 4, 8. We do not have a common difference, not linear.
So do all quadratics have to have a falling action?
No, some quadratics go up, some go down, but they all have a common second difference. not to each other within its own function. Now the last question on there at the very bottom of your page, how would you explain their growth compared to each other? Like which one grows faster?
Definitely B.
Exponential ends up growing faster. And here's why. We already looked at the Gini thing, right? It's doubling, doubling, doubling. I just want to point out these to you. 2, 4, 2, 4, and 4, 16. They do have a couple in common. But doubling something gets something real big. You're only squaring the next number up, right? So it's getting bigger, more than linear, but not near exponential at all. I'm going to go back to my computer because I want to show you these two functions on Desmos so we can compare them on Desmos. So here are the two functions we were just looking at. Remember, where did I say they were the same at? 2, 4 right there. And 4, 16 right there. That's what, look at your table, Bob. 2, 4, and 4, 16 match up. Okay, then, look what ends up being more. What starts a little higher? The exponential. Then what's higher for just a little bit? And then what ends up being higher forever? The exponential. And by an increasing amount. Look at that. Almost vertical, right? So that's happening because of the order of operations. Notice this one hits 0. The exponential function is not ever 0, right? Because you can't do 0 times something. All right, we're going to look next page. Let's get on the right thing on your slideshow here. On the back, you're going to compare these two functions, and you're going to see how they grow. I suggest a table. Compare these two functions on how they grow. Make a comparison. I suggest a table. Eyes up here. Mouths closed. I'm going to make some room down here because we're going to look at a table. I think the table is my favorite representation for this. So I'm going to do x and p of x. And I'm going to do x and q of x. And we're going to look 1, 2, 3, 4, and 5. I saw people making bigger jumps, and that's fine. Okay, so I'm going to put 1 into each function. 6 times 1 squared is 6. 3 to the first is 3. So which one's starting off more? P or Q? Okay, then 2 squared is 4 times 6 is 24. 3 squared is 9. So which one's still bigger? All right. Put a 3 in there. 3 squared is 9 times 6, 54. 3 cubed? Which one's bigger? All right, that quadratic's looking spicy. 4 squared is 16 times 6? 96. 3 times 3 times 3 times 3? 81. Ooh, what do you notice now, though? It's getting what? It's catching up. Okay. And last one. 5 squared, 25 times 6? 150. 3 to the 5th? 243, not 4. So what ended up happening? Yeah, so at the 5th step here, Q ended up bigger. What's going to happen forever now, though? Because this is triple, triple, triple. So big idea from this is, eventually, which one's always faster? Grows quicker. And here's why. This exponent, it's getting tripled, right? The exponent being high has a bigger impact. Remember that warm-up? We looked at small bases with big exponents. Okay? Here, does the multiplication happen first? No, squared first. Something times itself. 3 to something is times 3 times 3 times 3. So like the bigger thing only happens once each time here, the square. And then it's times 6. All right?
Would you say it would grow faster forever if it was parentheses 6x squared?
If it was 6x like this squared? I still don't think it would because you're only squaring it, right? You're only squaring the input. So it'd start much bigger, right? But eventually if you're tripling a huge number, you're getting a huge, huge, huge number, triple a huge number, right? Where this is just next step up still, squared, yeah. Exponentials are going to end up growing fast eventually, right? We know that the exponential function looks almost vertical at some point every time. Okay. Here's your lesson summary. Backed out your assigned seat. Homework's in the top basket when you finish.